Okay. All right. So we finished up Module 11 yesterday. So that Module 11 quiz, the participation quizzes from the last 2 days, actually the last 4 days, and then the Module 10 quiz will all be due at the end of the day, Sunday. Okay. So today's participation quiz, I've got it set to be due the end of the day, Sunday as well. However, we won't have a Module 12 quiz pop up until next Monday. But next Monday, we'll have 3 participation quizzes for Monday, Tuesday, Wednesday. We'll have that Module 12 and Module 13 quiz, both due at the end of the day next Thursday. So a little quicker turnaround on Module 13. I'm going to try to get through Module 12 a little bit quicker because I think if we can have some additional time for Module 13, that's going to be beneficial. I tend to think Module 12, some of it's a little bit easier, but we'll kind of take as much time as we need. Other than that, any questions for me before we kind of jump into things here today? Okay. All right. So we're really going to switch things up quite a bit today. It's not going to look, the last, I think, 4 classes, we've seen a lot of similar cost structures. We're going to be diving into a specific type of topic that applies to situations or arises in situations where we have a small number of firms. So before we really get too much of a market context, we'll have to talk about this concept, which is game theory. So we'll start talking about an equilibrium. We're going to be specific in that we're talking about what's called a Nash equilibrium, which is that everybody's currently best responding to each other's best response, or everyone's best strategy is the best strategy they can choose given all the strategies that everyone else is choosing, and everyone's choosing their best strategy. Right. So if you haven't heard of this before, this is you can go back, watch a great movie. Beautiful Mind is all about John Nash, who really, I shouldn't say came up with game theory, but really pushed game theory to be push the mathematical side of it. And so he's kind of known as kind of like the godfather, I guess. I don't know if that's really even the term that you would use, but he's kind of known as the guy connected with game theory. Okay. So the very basics that we're going to have, we're going to look at some very simple game theory examples. We're going to have players and rules. So for us, we're just going to do 2 players, right? We're not going to make it any more complicated than 2 players. The similar sort of approach that we're taking would apply if we had more than 3 players. It just becomes more complicated mathematically. We're going to look at when decisions are made. So we'll end up eventually, probably not today, but next class talk on Monday, talk about why it matters when people are making decisions. So are they making them sequentially? Are they making them simultaneously? So that's kind of our players and rules. Strategies is just going to be the different possible actions that a player can take. So I can, as a firm, set a high or a low price, or I can set the price to be 10, 9, 8, 7, 6, 5. I can have more than 2 strategies. Although for the sake of what we're doing, we'll kind of keep this simple at 2 strategy games. Okay. And then what's going to matter, we have the players who's making the decisions. We have the decisions or their choices that they can make, right? Their strategies. And then once people make these different decisions, what are the payoffs to each person? So you can kind of imagine in a market context, if 2 firms, right, those are our players, they can set a high or a low price. If they both set a high price, that's going to have a certain outcome and payoffs to both firms. If they both set a low price, that'll have a specific, if one sets high, one sets low, that could result in different profits for each firm. And so our payoffs are going to be ultimately how these players are making their optimal strategy choices, right? We still have the same sort of assumption, which is everyone's trying to maximize their profits, their economic profits. Or when we kind of think about this in less market-based examples, everyone's trying to maximize their own payoff. So this could be as simple as like there's a chicken game, if we're running at each other, you got 2 people, we're both running at each other. We have to make a simultaneous decision at the last second to either go left or right. If we both go left, yeah, not a good outcome, right? Payoffs are bad. If we both go right, payoffs are also bad. We run into each other. So they are kind of our optimal strategy. Hopefully one of us goes left, one of us goes right. That's going to result in higher payoffs. Okay. So we're going to represent these in normal form matrices. So let's say we've got 2 players, right? And I'm going to kind of use this market example to start out, and then we'll kind of look at some non-market based kind of game theory examples. So 2 firms, they can set a high or a low price, and then the resulting kind of payoff that's going to result from those different combinations. So this is how we would depict it. Okay. And in fact, I think I did this so it didn't muddy up the slides, but I put 1 and 2 here. Really, this is like player 1, player 2. We could call this, this was the firms in our example. So they both set a high price. They're going to have some resulting payoff, right? The way that we're going to kind of depict this is in the lower left corner, that's always going to be player 1, or in this case, firm 1's payoffs, right? So if they both set a high price, here's firm 1's payoff, here's firm 2's payoff. If they both set a low price, that combination of strategies would result in player 1 getting this payoff, or firm 1 getting this payoff, firm 2 or player 2 getting this payoff, and then the other kind of combinations of those prices as well. Okay. So this is going to be our payoff matrix, right? Now we're going to have actual values here in order to solve for what the Nash equilibrium of this game will be. Do both firms set a high price? Does firm 1 set a high price, firm 2 set a low price, etc. Okay. So the other terminology that we're going to use is when we start to identify what these players should do, if it's always optimal for firm 1 to set a high price, no matter what firm 2 does, we would call that a dominant strategy. Their strategy choice, the price they're going to set, does not depend on what the other person does. It's a dominant strategy. They're going to do it no matter what. Okay. So no matter what the other person does, if each firm has a dominant strategy, well, then we know what the outcome is going to be, right? If no matter what the other person does, it's always optimal for me to set a high price, and the other firm, no matter what firm 1 does, it's always optimal for them to set a high price. We know that both firms will set a high price. It's not going to be the most interesting games, right? But we do have those dominant strategies, and if both people have a dominant strategy, we end up with a Nash equilibrium, or what we call a dominant strategy equilibrium. Okay. Now, sometimes we end up with these examples where we have a prisoner's dilemma. Right? So we can have these Nash equilibrium where we end up in an outcome that's not actually where, if we could agree to make different strategy choices, we could both be better off. Okay. So we'll kind of look at some examples of this. Okay. So let's say I've got 2 individuals. We'll look at a non-market-based example, and then I'll maybe do a market-based one. Let's say Dan and Joe, suspected bank robbers, and they've got enough evidence to put each of them away for 5 years if neither of them confesses, right? Maybe they get them on lesser charges. Okay. They put them in separate rooms and offer them the following deal. If you confess to this bank robbery and you rat out your partner or you implicate, then you get to go free, right? And if you don't confess, but the other person does, you get 25 years. So there's this incentive. If I, implicate my partner, or I confess to this crime and they don't, I go free, they get 25 years. However, we're in separate rooms. If we both confess, well, they now have more evidence. They can not only put both of us away for 5 years, we both would get 10 years. So how would we depict this with this normal form game? So I've kind of got it all here, but I'm going to build this out for us so we can start to think about how we solve these games. Okay. So we had 2 individuals. Let me make sure I line this up. Who did I put on top? I put Dan on top, so just so that what I'm saying kind of lines up. So Dan and Joe. Joe can confess or not confess. Those are his 2 strategy choices. Dan can confess or not confess. So we're going to draw out this 2x2 matrix representing we have 2 players and 2 strategy choices. Okay. So I'm going to draw these diagonals. We kind of typically put player 1's payoffs in these bottom left corners, player 2 in the top right. So player 1, player 2. So we said if they both don't confess, they're only going to get 5 years. Right? If they both confess, they would get 10. If Joe doesn't confess, but Dan does, Dan goes free, 0 years in jail. Joe gets 25. If Dan doesn't confess, but Joe does, Joe gets to go free. Dan gets 25 years in jail. So this is kind of a weird example in that higher values here are a bad thing, right? More jail time is not preferable to these individuals. So if you wanted to, you could put negative signs and everything, or we can just talk through this. If we're trying to minimize the amount of time that we spend in jail, we want to choose the lowest value here. Okay. So the way that we would solve these games is go through for each player and determine what their optimal response is to both of the strategy choices of the other individual. So this is how I typically do it. I would draw it out, or if I had it like on my, if I guess I'm on a screen or something, I would say, okay, look, let's assume Dan confesses. Okay. So if Dan confesses, I'm not good at drawing my left hand. So if Dan confesses and Joe confesses, he gets 10 years. If Dan confesses and Joe doesn't confess, he gets 25. Which of those is preferable to Joe? If Joe is choosing between these two outcomes, responding to Dan confessing, it's better to also confess and get 10 years as opposed to 25 years in jail. Now, what if Dan instead is choosing the other strategy, which is to not confess? Well, then what should Joe do? If he confesses, he gets 0 years. If he doesn't confess, he gets 5, right? Which of those is better? 0 years in jail is better than 5 years. Okay. So here we have an example where the strategy choice of Joe is always the same. No matter what Dan does, it was always better for Joe to confess. Okay. I keep forgetting that second S for some reason on the word confess. So we now have to determine what are Dan's best responses. So Dan says, okay, if Joe confesses, should I confess or not confess? Well, 10 years in jail is better than 25, so he would choose to confess. What if, my hand's too big, I guess. What if Joe doesn't confess? What should Dan do? Well, if he confesses, he gets 0 years. Doesn't confess, he gets 5. 0 years in jail is better. So we end up saying here, Dan also has a dominant strategy to confess. No matter what Joe does, it's always better for Dan to confess. So this is the non-technical way of saying this. But anytime if you go through and use this circle system or you underline to identify the best responses, anytime you have 2 circles in the same box, or each person's best response to what the other person is doing, so we are both best responding to each other's best response. That would be our Nash equilibrium, right? So here, because we had dominant strategies, we know that no matter what the other person does, it's always optimal for both people to confess. We end up with this dominant strategy Nash equilibrium, which is they both confess. Okay. Any questions there before I then kind of add one more thing in? So not only is this a dominant strategy Nash equilibrium, we would also say this is an example of a prisoner's dilemma. So a prisoner's dilemma is we end up in a Nash equilibrium where the payoffs to both individuals are worse than if we could agree to make different choices. So notice here, okay, if instead Dan and I agree that Dan's going to confess and I don't, well, I get 20, I'm not better off here. Okay, so that doesn't make it a prisoner's dilemma. However, if we both agreed not to confess, what would be true about the payoffs for both individuals? They would both get less jail time. So anytime there's another outcome that isn't the Nash equilibrium that results in better payoffs for both people, we would call that our prisoner's dilemma. Okay. And, set up this example with prisoners, right? That's kind of where it comes from. So we went through, we identified what Dan's best response was to Joe confessing, what Dan's best response was to Joe not confessing, and then what is Joe's best response to Dan confessing, and then what was Joe's best response to Dan not confessing. We ended up with this Nash equilibrium, right? Oops. Which is that both individuals confess, and here, did I change this? Yeah, I did change this. Sorry, I changed my example, the numbers for a reason here. So I've got 10 years instead of 8. It doesn't really matter. We would have actually had the same Nash equilibrium if we did that. So they would have both been better off if they had both remained silent. So this was our example of a Nash equilibrium, but also a prisoner's dilemma. Okay. So this kind of seems like maybe a goofy example thinking about prisoners in jail, but the same sort of logic would apply if we're thinking about companies, right? Trying to agree to work together to act as though they're a monopolist. Okay. So I said last class, but T-Mobile, Verizon, I think this was, I kind of moved these out of order. We talked, I think I changed my example that I was going to do for a monopoly where I had like two firms acting like a monopoly. So let's just ignore that last class thing. But if I had T-Mobile and Verizon, and let's say it's a duopolis. So there's they're the only two firms, and they both agree, right, to produce a quantity of 30. If they do that, they'll be at the monopoly kind of optimal profit maximizing quantity in the market. Okay. So we're going to look for this Nash equilibrium, right? Which is, okay, is each firm, they're choosing the quantity that maximizes their total economic profits. So we kind of have this scenario where let's think if each firm is producing 40 units, right? And kind of what the kind of corresponding best response would be. So this is kind of our setup, and then we'll kind of come back to thinking about this. So I could, in theory, choose a bunch of different quantities here. So I've only kept it at 2 to keep this game simple. In reality, firms have production decisions, from 0 to however many units they can produce. Here, I'm just thinking about a low versus a high quantity. And the same principles would apply if we had more choices. So we'll just kind of look at just 2 choices, okay? So if they both restrict quantity, right? And I'll kind of draw a graph out to go along with this here in a second. This is going to be the quantity in the market. Well, yeah, so this would be the quantity in the market, each producing 30, a total quantity of 60. That would be what a monopolist would choose, to produce 60. We have 2 firms, they'll both produce half of that, and so they're going to get the market to that monopoly quantity. If they do that, both firms earn $900 in profits. Here, if both firms were to produce 40 units, right? Well, that's a little bit higher, right? 40 plus 40 is 80. It's higher than the monopoly profit maximizing quantity. So they'll both be earning profits, but their profits will be a little bit lower. Okay. However, if the other firm sticks true to this agreement and produces 30, but I produce a little bit more, well, we know that the overall quantity in the market would go up, which means it'll drive the price down. So this firm would experience a price effect, their profits go down. But here, this firm gets a price effect that pushes profits down, but an output effect that increases their profits. So potentially, by breaking the agreement, if the other firm doesn't, I can actually increase my profits and theirs would decrease. Okay. So why is this an example of a prisoner's dilemma? So I'll kind of write this one out too. I think it helps maybe to see kind of, I don't know, using my hands. If I'm making that up, then just bear with me. So we had what? Verizon, kind of T-Mobile. They're making production decisions. And we had what? So, I got this. We had 800, 800. I think this was 700. No. Well, I think this was the values. And this was 1,000, 750. And this was 750, 1,000. Let me make sure I have those. Are those the same payoffs that I had? Oh, nope. What did I do wrong here? Sorry, this was 800. These were 900. Okay, I looked at that wrong. Okay. So if we determine the best response of both of these firms, okay, first I'll do T-Mobile, right? If Verizon chose to set that quantity at 30, so they stuck true to that monopoly agreement, what should T-Mobile do? Well, 1,000 is better than 900 if these represent profits. So they would actually choose to produce 40 units. What if Verizon broke the agreement and they didn't produce 30, they instead produced 40? Now what should T-Mobile do? Well, they should also produce this higher quantity. If they don't, they're experiencing that negative price effect without any additional output effect. And then we could say, okay, if T-Mobile sticks true to this agreement, what's the best response for Verizon? Well, 1,000 is better than 900. If T-Mobile breaks the agreement, what should Verizon do? 800 is better than 700. Now we end up with, where's our Nash equilibrium? both firms actually break the agreement and produce a higher quantity. So how can we connect this to what we were looking at last class? So we can think about this as when I'm looking at this demand curve, right? And then there's some overall marginal costs. We were thinking about this as that point where the monopolist would choose would be at a quantity of 60. Right? So this represented when we were both producing 30, what would the total quantity be in the market? Remember, this is the market, not each individual firm. So if we're both producing 30 units, we'd be up here setting that monopoly price. Right? In this example, whatever monopoly profits were, we would then split them evenly. Right? So in this example, if we're both earning 900 profits when we produce 30, so we're acting like a monopolist together, that means, if we each producing 30, half of the quantity, what would half of profits be? Each firm's payoff. So we would kind of have like monopoly profits here were at their highest, or 1,800. Now, we see that there's this Nash equilibrium where both firms have an incentive to break the agreement, and we end up with the Nash equilibrium being we both break the agreement and produce a quantity of 40. Well, if that's the case, if we both break the agreement, what's the total quantity in the market? That would be 80. That's going to result in a lower price, so call this like the second price here. And that gap in between our price and average total cost, it must be that that's driving profits down, because now what is the total amount of profits made in the market? Only 1,600. Okay. So this is a problem because I said these aren't the only two production decisions I can make. I would really, in theory, have like a quantity of 50, 60, 70, 80, 90. And what's going to be true at every single quantity, there's always the incentive to be the one that produces a little bit more, right? And that's going to occur until we get down to this point where profits are now equal to zero, right? I'll kind of use this and kind of show you what that would look like, right? So once we get down to, let's say, quantities of like, I don't know, 190 to 200. So if they're both producing 200 units, let's say that quantity that the perfectly competitive market would choose is 200. Or actually, sorry, they're both producing 200, so that would be 400. Right? So at that point, we know they're both earning zero profits, right? There's no profits to be made. If they would produce a little bit less, maybe they would both still have, I don't know, $150 of profits, right? But there's always going to be this incentive, right, that kind of pushes these firms down here. If I'm the one producing more, I would get a little bit higher of a payoff, right? So what do I want here? Oh, no, these aren't the values. Well, I can make the point here anyways. So I go through, I identify their best responses. So it looks like it's here. Now here they're indifferent, right? Because they're at zero in either scenario. I then kind of have this one. So, oops, yeah. So at this point, I could get, okay, once I get towards that, that point where profits are zero, I might have a tie. So I can have like firms being indifferent between these two production decisions. And here I could actually have an example, if these were the payoffs, where I have multiple Nash equilibrium. So in the examples I looked at up to this point, we only had one Nash equilibrium. We can have multiple Nash equilibrium, in which case we come back to this stupid answer that we sometimes get in economics, which what is the ultimate combination of production going to be here? Indeterminate, right? If we've got multiple equilibrium, we don't know which one we're going to end up in. Okay. All right. So that, hopefully we can kind of see how some of this game theory stuff is relating to what we talked about before. So with that in mind, right? So we had our T-Mobile example. We went through, identified the best responses. We said this will be the Nash equilibrium. It's a prisoner's dilemma because if we could agree to produce less, both individuals could get higher profits. However, we know they won't. There's always this incentive to be the one that breaks the agreement if we're making these decisions simultaneously, and we end up with this outcome that's worse for both companies. So we could look at this in kind of a graph form as well. And here we have to remember when we're talking about these examples, we're talking about two firms. So they're acting together as a monopolist. They've got constant marginal cost of 50. Here's their price and quantity. This is the demand curve they face. If I didn't give you revenue and marginal revenue here, you could actually solve this model, right? Because what is revenue? Price times quantity. That's all I did there. What's marginal revenue? The change in my total revenue divided by a change in quantity. Well, here I don't just have nice quantity jumps of 1. I've got 1,000. So, you know, a little bit more math to do. But I can see here I've got this downward sloping marginal revenue curve. Just to reiterate some of the things we talked about before. What's the slope, right? Or kind of think about as the quantity goes up by 1,000, price was falling by 10. Notice as quantity goes up by 1,000, what is marginal revenue falling by? Should be twice as steep, so it falls by 20. So where would the perfectly competitive market be at in the long run? Okay. Well, if, right, there's always this incentive for me to be the one that produces a little bit more, we end up at this point, excuse me, where our marginal cost is hitting the demand curve. So to kind of give a visual of this, we said, if we had constant marginal cost at 50, if this was a truly perfectly competitive market, that marginal cost of 50 would represent kind of market supply. We should end up at this point, right? This would be the perfectly competitive quantity. How much would each firm be producing? Whatever that quantity is, divided by 2. Okay. So if we're thinking about the perfectly competitive market, where would marginal cost be equal to the demand curve? That would be where the price is equal to 50. Okay. So price is 50. Total quantity in the market is 1,100, right? So if I'm thinking about the competitive market, what's the price and quantity? It's going to be 50 and 11,000. However, if I'm thinking about, where am I with this? Let's go ahead. Well, I didn't add this one in. If I had an additional question where I asked how much is each firm producing, well, if the total quantity in the market is 11,000, each firm would be producing 5,500. Okay. So we've got this scenario where the quantity in the market was 11,000. So then the quantity that each firm produces would be half of that, or 5,500. Okay. Now let's assume those two firms agree to come together and work as a monopolist. Okay. If they do that, they'll make decisions based off of or they're going to set the quantity in the market based off of this twice as steep marginal revenue curve. Right? So the quantity that the monopolist would choose would be here. We go up to the demand curve to figure out that price. Now in this scenario, I didn't add it in, but what would the price be if I had constant marginal cost for that perfectly competitive market? Whatever that marginal cost is. Okay. So where does that marginal cost of 50 equal the marginal revenue? Looks like right here at a quantity of 6,000, right? However, that's 6,000 total units in the market. So I just identified, just like we did last class, from that demand curve and a constant marginal cost, where the quantity of the monopolist would be. However, what's the quantity of each firm in that scenario? It would be half of the total quantity in the market, or 3,000. Okay. And then what would the price be? Well, at that quantity in the market of 6,000, what's the price? $100. Okay. So you can kind of think about here, just kind of filling out our visual to go along with that table. Okay. Now, what's a little bit, so this was the quantity in the market. If I then asked you about how much does each firm produce, you would go about it the same way. You would still identify the market quantity and the corresponding price, but now each firm, that price will be the same, but the quantity they produce, they're one of two firms, it'll only be half of that. Okay. So just a couple things to kind of reiterate here. We could actually, oops, look at this example, right? And let's take these situations, and let's, for the sake of this, to start out, just think about, I could set two quantity values, okay? So if I tried to convert this, give myself some more room here, into a normal form game. So I have two firms. Firm one, they can set the quantity at 5,500, or they can set the quantity at 3,000. If those were their two choices, so they can agree, act like a monopolist with this other firm, or they can kind of break that agreement, act like a perfectly competitive firm. Okay. So got separating our payoffs. We know, and here I won't even, I can kind of come up with some hypothetical, well, actually, I can come up with some actual values here, right? So if I were to calculate profits here, total profits in the market, if this was a monopolist, would be what? Profits are equal to price minus average total, but we said when we have constant marginal cost, that's the same as average total times quantity. So what? Each firm has 3,000 units. Difference between their price and average total cost is 50. So I get what? They're both acting like, so 15 and 4 zeros. So 150,000 each. Okay. Now, if they both set the price at 3,000, kind of an extreme, or sorry, quantity at 3,000, what are my total profits here? 0, right? We're at that perfectly competitive outcome where we know profits are equal to 0. Okay. Now, this other one, these other two examples would be, what if one of these firms breaks the agreement, but the other doesn't? So that would be something like, okay, if I'm producing 3,000, the other firm is producing 5,500, what's the total quantity in the market? The total quantity in the market in that situation would be, what, 8,500? So we know the resulting price will be lower. We don't know exactly what it is without more information, but it'd be something like this, right? So what's going to happen is the firm that is still producing 3,000 units, the difference between their price, this new price, and their marginal cost is now lower. So now they might only have like half as, if the price got cut in half. If I'm the one that produces a lower amount, my profits are going to go down. Now, the other firm, even though their profits are going to go down because the price fell by, got cut in half, if they're producing a higher number of units now, 5,500. Oh, I flipped these. Hold on. No one called me out on this. Okay. I was writing this in. What did I mix up here? If I'm talking about a monopolist, what should the quantity be? The quantity should always be lower. So I should have these kind of flip-flopped here. So let me draw this out again, and I'll kind of talk. Sorry, I'm talking and I'm writing, and I need to make sure I'm looking at what I'm doing. So we had firm one. This is what I meant to do. Let's put the monopoly quantities up here. And then the perfectly competitive quantities would be when we're producing more. Sorry about that. Oh. Okay. This is why sometimes I probably should rely on the slides, but I think seeing this stuff by hand is helpful. So when we had monopoly profits, that's where we said both was earning 150,000. If they act like a perfectly competitive firm, that's where they're 0. Okay. And then if I'm the firm that produces the same number of units, but the other firm produces more, well, that's going to lower the price. So maybe now my profits are only 75,000. However, the other firm, even though their price is lower, they're selling way more units. So potentially their profits would actually go up in that scenario. And then same kind of idea here. If firm one sticks true to the agreement, they're going to keep selling the same number of units, but at a lower price. So their profits would go down. Firm two, yeah, they're selling at a lower price, but they're selling a lot more units. So potentially now their profits are 200,000. Okay. So if we were going through this, what is each firm's best response? Well, firm one, right? If they're choosing 3,000, what should firm two do? Well, 200,000 is better than 150. And then if firm one is choosing to produce the higher quantity, what should firm two do? Well, here I've got 75,000 is actually greater than 0. Okay. And then we could kind of go through the same thing. What if I had a firm over here? So now 3,000, which was larger. And then over here, which of these is larger? I could actually end up with a scenario where potentially if the payoffs were right, I have multiple equilibrium, and I know one of the firms will break the agreement, but the other won't. Right? Now, what's probably a little bit more practical, right, is that if I had this same setup, what's more likely to be true, and here we're just solving more games here, so this is good to kind of get this. Oh. So we had 0 at that perfectly competitive point, 150,000 if we're acting like a monopolist. What's probably more likely to be true is that if I keep selling the same number of units and the other firm produces kind of a higher number, that demand curve, the steepness of it is likely going to be steep enough where that reduction in price, right, isn't going to just be that it cuts profits in half. It's possible, right, that if I'm thinking about an average total cost curve here, right, that at that newer price, it only generates profits for maybe the firm that breaks the agreement, but causes negative profits for the firm that doesn't. Right? So if that's the case, right, the firm that doesn't break the agreement is now earning negative profits. Well, now when we solve this model, what's the best response of firm one if firm two holds true to the agreement? Well, 200 is greater than 150. What if they break the agreement? 0 is better than losing 75,000. What about firm two? If firm one holds true to the agreement, 200 is greater than 150, 0 greater than 75. Now we've got a Nash equilibrium that is a prisoner's dilemma because both firms are going to be worse off in this Nash equilibrium than if we could agree to stick true to that agreement and act like a monopolist. If potentially we had a scenario like this, well, there is going to be an incentive to kind of be the one that breaks the agreement, but these wouldn't be an example of a prisoner's dilemma, because if we were at a different outcome, yeah, one of us would be better off, but one of us would be worse off. So it has to be that there's another outcome other than the Nash equilibrium where both of us are better off in order to be this prisoner's dilemma. So this prisoner's dilemma is going to drive, in most cases, drive these firms away from that monopoly agreement and move them towards that perfectly competitive quantity. Okay? So for consumers, this is a good thing, right? We would love it if the game looks like this, because we know then firm profits are going to go to 0, consumer surplus will go up, deadweight loss is going to go down, right? And we end up at that perfectly competitive point. Okay. All right. So I added quite a bit in there. Let me look and see where we're at. And we kind of went through this duopoly cooperation games. Let me think what else I want to do here before. Well, I'll kind of point this out. So which of the following, if I'm thinking about if they did stick true to this agreement, why is that likely not going to last? Well, if either firm has this dominant strategy, which is to always be the firm that first breaks the agreement, then it's always going to push us to that Nash equilibrium where payoffs are lower. Okay. So if we have dominant strategy equilibrium that result in these prisoner's dilemmas, it's likely we're not going to see these two firms hold true to the agreement. They're actually going to break it, end up at this point where we said the quantity they produce is the perfectly competitive quantity. Okay. So it's not that there's necessarily more competition. It's just that there's always this incentive to be the one that breaks the agreement first. Okay. So this is kind of a goofy question, really kind of highlighting this idea that what is pushing us away from firms acting like a monopolist together? It's the incentive that exists from being the one that breaks the agreement. Okay. Before we go to the quiz, I'll think of this in a slightly different way to get at this point. So let's, instead of quantities, right? Let's think about, I can choose kind of two prices. So we'll think about the most extreme kind of scenarios. So I'll start out with, and here I'm going to show you another way that I'll sometimes draw these normal form games that I think makes it a little bit easier to work through. So here's firm one, here's firm two. Instead of these kind of like diagonals, sometimes we'll just write firm one's payoff first, firm two's payoff second, and separate them with a comma. So let's assume that we had this example where if we're both setting a higher price, I don't know, maybe we're earning profits of 100,000 each. Okay. Selling the exact same amount, consumers are indifferent. They don't care if they buy from firm one or if they buy from firm two. If we're both selling at a lower price, right? Let's assume that we're out here on a portion of the demand curve where, remember, if I, well, I don't want to complicate this. Let's just stay with here for right now, and then we might come back to this later. So let's say they both charge a lower price, right? So yeah, they might be able to sell more units, but that's going to push us kind of closer to that perfectly competitive profits of zero. And so if we're both charging a lower price, maybe we're only earning 50K a piece. Okay. We're selling more units, but at a significantly lower price, and now our profits are lower. Okay. In an extreme scenario, if these are perfect substitutes, they're producing the exact same good. If firm two charges a higher price, firm one chooses a lower price, who is everybody going to buy from? Firm one. Okay. So everyone's going to buy from firm one. Maybe now they'll make 200,000. How much is firm two going to make? Well, you know, in theory, even if they could avoid all of their costs, if nobody buys from them, what would their total revenue be? Zero, right? And then here, if firm one is charging a higher price, firm two is setting low, maybe everybody buys from firm two, so 200,000 goes to firm two. Firm one is going to make nothing. So if we were to solve this game, what should player one do if player two sets a high price? Well, payoff is higher if I set a low price. What if firm two is setting the lower price? Well, then what should I do? Also set the lower price, right? No one will buy from me if I set a higher price. And then what if firm one is setting the high price? Firm two should set a low price. If firm two sets a low price, firm one sets a low price, what should firm two do? 50 is greater. So what do we end up with here? A dominant strategy Nash equilibrium where both of them charge a lower price. And this would kind of continue. Like, I'm going to keep this at two strategy, two-person games, but you could actually add in a third choice, right? So, well, what if I could lower the price even more? And then you would have all your payoffs, and you would kind of continue to kind of do this comparison. It gets more complicated. I won't give you a three strategy game. I'll kind of only keep it at this two. But even with just two price choices, we can see, because there's this incentive to be the firm that breaks the agreement first, it's going to push that market to a lower price or towards that long run perfectly competitive equilibrium until profits are equal to 0. Okay. Got some fire alarms going off. Hopefully that's just a test. It's noon. So, um, so we'll come back to this in a second. Well, I think what I want to do here for the sake of time. So we should have plenty of time tomorrow to get through all this. So yeah, let's take a look at the participation quiz for the day. Just has more games that we can look at. Okay. So I said, sometimes we won't have these games where I'm kind of using this like diagonal, the kind of triangle view of it. I'll just put firm one's payoffs first, firm two's payoffs second. Okay. So if I had a game that looked like this, right? What is going to be the equilibrium of this game? Okay. So United and American are our two players. We can cut or not cut pairs. I'm going to draw this out. Well, make sure I get the same values that are up here. So 400, 400, 800, 200, 200, 800. And you can do this on a screen. I also think that it probably helps in a lot of these to draw it out for yourself. So we're first asked about kind of what that Nash equilibrium will be. We then got a different example here. So let's do this American one. It kind of already went through one like this for us, but just seeing this more times I think is helpful. So if American decides to cut fares, United, player one, where is their payoff higher? If they cut fares as well, 400. If they don't cut their fares, everyone buys from American. So this is their best response. If American doesn't cut their fares, what should United do? Here's their best response. And then if United cuts fares, what should American do? Also cut their fares. If United doesn't, what should American do? So once again, it doesn't matter what the other person chooses to do. American will always cut fares, so will United. So we have this dominant strategy, Nash equilibrium. And we would also have an example of a prisoner's dilemma, because if we could both agree to keep our rates high, we'd be at this outcome where both individuals would be better off. Okay. Any questions on that idea? Okay. So how would this not be an example of a prisoner's dilemma? So let's say I had a similar setup. Let's say I got 400 here, 400 here. Oh. Let's say I had. So let's say the game looks something like this. Well, we could go through and solve it just like we did before. So for person one, if player two, this is United American, doesn't matter. I'm just going to give them numbers here. What should they do if player two cuts fares? Well, 400 is greater than 200. What about over here? 800 is greater than 300. All right. Now, what if player one was choosing to cut fares? What should person two do? What should person one do? So now we have the same dominant strategy, Nash equilibrium, but is this an example of a prisoner's dilemma? No, because any other outcome, well, here, this person would be worse off. Here, this person would be worse off. And if we move to this outcome, both people would be worse off. We don't have a prisoner's dilemma example here. It's only a prisoner's dilemma if there's another combination of strategies where both individuals would have higher payoffs. Okay. Any questions before we keep moving here? Let me think. So let's instead do the second example. So that first one was that we had this Nash equilibrium where they both cut fares. So let's say instead I've got person one, and we can also put this not in like market context, but we can also look at like worker decisions. So there's this word in economics called shirking. Basically, just means you're slacking off and you're not working hard. So let's say I used to work at stocking a grocery store, and I probably have mentioned that at one point in the semester. But when you're working with other people, right, and there's things that need to be done, if one person works hard, I can rely on them. I might be able to slack off a little bit and the job still gets done, so I still get paid. I don't care, right? So let's think about here, if person one is making this decision to either work hard or not, and person two is also working hard. Okay, well, if I work hard as well, I'm going to get a total payoff of 10. So maybe this isn't like dollars. This is like I get some level of utility or happiness from like when the other person is working hard. If I'm also working hard, I feel good about myself. If I don't, yeah, it's nice to not work hard. I get some value from that, but that value is not near as high. Like I now feel like there's this unequitable distribution of work. And so the higher payoff here would be if I also work hard. Now, if the other person is slacking off, well, now if I also slack off, well, I like not working, but at the same time, I want to keep my job. So even if the other person isn't doing their job, maybe I get value from just like making sure the job gets done the best it can. So here, their best response to the other person not working hard or shirking would be that they still work hard. So player one has a dominant strategy to play to what? Choose to work hard. What about person two? Well, person two, if player one or person one is choosing to work hard, well, maybe, they want to make sure the job gets done. They value that, but they also really value being able to relax, right? So if they don't work hard while the other person is, they're not really bothered by this very much. They don't care that there's unequitable distribution of work. They really value that they don't have to work, right? Well, what if the other person is slacking off? Well, here, okay, I really value not having to work, but if the other person isn't working as well, and I might lose my job, well, I need to make sure that job gets done. So there I'd choose to work hard. So here's an example where player one has a dominant strategy, but notice player two, their choice depends on what the other person is doing. If person one works hard, they're not going to. If person one doesn't work hard, they will. Okay. So we wouldn't have a dominant strategy equilibrium. Notice now, where is our Nash equilibrium? Where are we both best responding to what the other person is doing? Person one is going to work hard. Person two is not. Right? And would this be an example of a prisoner's dilemma? There's no other outcome where both people would be better off here. So we don't have a prisoner's dilemma. Okay. So there we're going to see player one choose to work hard. Person two is going to choose to shirk. Okay. All right. So third and final game we have here in this quiz is going to be firms setting higher or lower prices. So we can both set a high price or a low price. We got 10 million, 10 million, 5 million, 15 million, 7 million, 7 million, 15 million, 5 million. So sometimes we'll have like what we would call, if I can get this out of here, right? Oh, what am I blanking on this word? Oh my gosh. Sometimes we'll have situations where the payoffs to both individuals are the same in all these different, right? They're like mirror images of each other. Sometimes we don't, right? So in the case where we do have this type of payoff, right? We can solve these games, right? So if person one is choosing to set a high price, okay, what should person two do? Well, they set a high price 10, low price 15, so that's their best response. If person one sets a low price, what should they do? Well, 7 is better than 5. Right? If person two sets a high price, what should person one do? Set a low price. If person two sets a low price, what should person one do? Also set a low price. This was an example that we already looked at where we said both firms have a dominant strategy to set a low price. Okay. This Nash equilibrium is not going to be the outcome that maximizes profits for both firms. So it's an example of a prisoner's dilemma, right? So we're thinking about that third question. Which of the following is not true? Well, both firms have a dominant strategy set a low. Okay, that we said both had a dominant strategy set a low price. It is an example of a prisoner's dilemma because that made our Nash equilibrium low price, low price. If they could agree to set a high price simultaneously, they could both be better off. The equilibrium is going to maximize total profits. Well, that's prisoner's dilemma, and then this one would go against each other completely, right? So because this is a prisoner's dilemma, we know that this will not be where total profits are maximized for both firms, so that one's not true. And then firm one and firm two will not cooperate to set a high price. That one's true because we said this would be the Nash equilibrium where they both break that agreement. Okay. So we had not, the one that's not true is that total profits are maximized at the Nash equilibrium. In our second one, we said person one is going to work hard, person two shirks. And then in our first example, we said that we have this Nash equilibrium where they both cut fares. Okay. All right. So some other examples that we see pop up with the prisoner's dilemma, just to kind of make this point, it's kind of interesting. You could do a similar sort of thing, but think about how much money you're spending on ads, right? So, there's always this incentive to be the firm that spends a little bit more on advertising, as long as we assume that advertising is pulling in more business. So even though I'm increasing my costs, I'm pulling a lot of business away from the other firm, but both firms have this incentive. So what ends up happening, we both spend money on ads, they equally offset each other. So maybe before, we were splitting demand evenly. Well, we're splitting demand evenly again, but what have we done? We've increased our total cost. So you could kind of think about it this way. When I'm thinking about advertising, there's always going to be this incentive to be the one firm that spends more on advertising, because if we did, so let's do an easy, let me see here. So here's my marginal cost, average total. So, let's even assume we're working together as a monopolist. So our production decisions is where marginal cost is equal to marginal revenue. Price is going to be up here. So we're sticking true even to our agreement to act like a monopolist with this other firm. But if I spend money on advertising, I know that more of that overall quantity, more people are going to want to buy my product. So potentially, right, I could, if I'm the only one who spends more money advertising, I'm going to get a larger amount of this quantity. I'd increase my profits. The problem is if the incentive exists for both firms to spend more on advertising to pull in more business, well, if we're both spending, we still evenly split demand. And what happens? Well, if we spend money on advertising, it's like a fixed cost. All we've done is increase our average total costs, in which case maybe now profits are negative, right? We could spend ourselves, that's an extreme example, but we could spend ourselves into negative profits if we're both having this incentive to spend more money in advertising where we equally offset each other, right? All we've done is increase our costs, haven't changed our revenues at all. Okay. OPEC is another great example of countries that try to act like a cartel. I haven't really honestly looked at the most recent data, but my guess is that there's a lot of these these countries who've agreed to this, if we didn't have some organized body checking them, right, it's always going to be beneficial to be the one that breaks the agreement first. Okay. And I think we'll talk a little more about what if we have not just a snapshot, a game played one time. What if it's played year after year? We'll kind of revisit this example. I believe next class we should have some time for that. Another good example is spending money on your military. It's always better to be the country that spends a little bit more on your military, right? However, every country has that incentive, so we both dump all this money in the military. However, because everybody has a strong military, no one attacks each other, so we haven't really gained anything, but we've increased our costs a lot. And then common resources, excuse me, right? If I had like fish in a pond, right, we should all agree to maybe only catch one fish a day. And that way the fish population could repopulate itself and there'll be, fish in the pond for the next 100 years. However, if it is a true common resource, we said what can happen? We get this tragedy of the commons, which is every person has the incentive to break the agreement. Instead of catch one fish, well, I want more free food, I might catch two fish. But if we all catch two fish out of the pond, they can't repopulate, and then that common resource goes away. Now we're all worse off, right? Now our payoffs are zero. We don't get any fish. Okay? So common resources are really when we've already talked about where we see that prisoner's dilemma pop up. So, is this a good or a bad thing for society? If this prisoner's dilemma does exist with firms' cost structures, it's a good thing for society because there's always going to be an incentive to be the firm that sets a slightly lower price or the firm that sells or produces a slightly higher quantity. Well, what is that doing? We said the monopolist chooses a lower quantity, higher price. So if there's incentive to be the one that sets a higher quantity and a lower price, it's just moving us towards that allocatively efficient or that perfectly competitive outcome, that perfectly competitive quantity and that perfectly competitive price where price is equal to average total cost is equal to marginal cost. Profits of the firms are zero. Deadweight loss goes to zero. Consumer surplus would increase. Okay. So good thing in terms of the markets, maybe not always a good thing, in terms of like these other examples, because, oh yeah, the whole thing with the prisoner's dilemma in the market is that it's shutting down monopoly power. But, in these other examples, what am I doing? I'm getting an increase in the number of, strong militaries. Maybe I end up seeing that there's more war, or I get the overuse of a common resource. So it's not always a good thing, but in the context of our markets, right, it is. Okay. So I got a political example. We've done a lot with the prisoner's dilemma today, so I kind of want to give you some slightly different views of this. So got 12 minutes. What do I want to run through today? I'm going to skip ahead a little bit. So we're going to skip these negative attack ads. It's not overly interesting. It's just another example of a prisoner's dilemma where we see it's always good to be one that runs negative ads while the other doesn't. And then we'll skip this. We'll save this for next class. But I did want to kind of go through this example because I think it's interesting and also highlights some facts. Okay. So let's say that we had a research and development example, and we're thinking about firms are putting money into research and development. All right. So I've got this general setup where if one firm puts money into R&D, all firms are going to receive $10 million. Okay. Well, that's, it's the idea that if there were no patents, right? So if one firm puts all this money into R&D, there's no patents, the other firm can steal it. We both earn an additional 10 million. However, the firm that spent money on R&D had to spend $9 million. Okay. If both firms do research and development, well, they might come up with different cost-cutting techniques or different new products. And so maybe now if both of them spend 9 million, we would see each of them receive an additional 15 million. Okay. And then I didn't say, but if nobody spends money in research and development, what happens to our change in profits? Nothing. Okay. So I can kind of think about this scenario where, let's say I had two car companies. If we both put no money into research and development, we're earning nothing. Okay. If Toyota puts money in, Toyota puts money in, but Ford doesn't, well, Toyota had to spend 9 million. They make an additional 10. They're up $1 million. Well, what if Ford didn't spend money? They have zero additional cost. They steal the technology, increase by 10 million. So we kind of have these different payoffs here. And then if they both put money in R&D, we said they would both make $15 million extra, but it cost them both 9. So they'd be both up an additional $6 million in profits. Okay. So if I go through and solve this model, right? If research and development, if Ford is choosing to put money into research and development, what should Toyota do? Well, 10 million is greater than 6 million, so they won't put money in. Well, what if Ford chooses not to put money in? Well, Toyota, if they put money into research, 1 million greater than 0, so they would select this, right? And then what about for Ford? Well, if Toyota is putting money into research and development, what should Ford do? 10 million is greater than 6, 1 million is greater than 0. So we actually end up with what we call a chicken game. This is kind of the one I mentioned at the beginning of class. A non-market-based example is if we're running at each other and we both at the last second have to decide, do I go left or right? We're making simultaneous decisions. We don't both want to go left or both go right. We have multiple equilibrium. So here I've got multiple equilibrium. Now which one am I going to end up in? I don't know, but whichever one I end up at, right? There's no other outcome where both people are better off. Notice here, like firm 2 wouldn't be better off, even though firm 1 would be. Here they would both be worse off. So what's the good news here? Well, one company puts money into research and development, right? That's going to be whatever equilibrium we're in. We get one of them puts money in. However, we're not getting both to put in. So if we were factoring in, like, we're not thinking about things like consumer surplus in this game, well, consumers might be losing out because they'd be better off if both companies were coming up with new products, cost-cutting techniques, putting money into this research and development. Okay. So previous example, we had 2 Nash equilibrium. It's kind of a classic chicken game, right? Where you can kind of write, if we both go left, we both go right, what are the payoffs? I think for the sake of time, I've got this example where we have multiple equilibrium. I want to point something out here. So what if I had the same setup, but I had patents that if I am the one that comes up with this new product, the other person can't use it? Okay. So if that's the case, right, then essentially, when we only one firm, the other payoff of the firm would be 0. Okay. So if that was the case, we're thinking about here's our 2 decisions: put money into research development or don't. Said if they both don't put money in, nobody makes anything, right? We had firm 1, firm 2, or Toyota and Ford here. So if firm 1 puts money in, right? They spent 9, they made 10, they get an additional, what did we say? 1 million, right? The other firm now gets 0. Or sorry, doing the wrong one here. If they put money in, the other firm doesn't, 1 million, right? And 0. Same kind of idea down here. If I don't put any money in, I get 0. The other person gets 1. Okay. So, well, what do I want to show you here? I don't want to do this. I might save this for next class because I didn't talk about that yet. We'll save that for next class. I'll show you another chicken game example, right? So just to kind of get another game that has multiple equilibrium, right? Sometimes I get ambitious, but I forgot we haven't talked about one other thing that I need to show you that. So let's say we have this example where both these 2 individuals running at each other, they can go left, they can go right. If they both go left, they crash and the payoffs are negative. They both go right, crash, payoffs are negative. Right? If they both go left and right, we could even think about this scenario where, well, I don't really care. We didn't crash, but it doesn't really make me happy or anything. I get no utility. So let's say the payoffs were 0 there. So this is a scenario, right? We can kind of think about, what should I choose to do? Well, if person 2 goes left, I don't want to crash into them. 0 is better than -10, so 0. What if they go right? Well, 0 is better than -10, so 0. The other person goes left. What do I choose to do? Well, 0 is better than -10. 0 is better than -10. Our research and development game was basically just a different form of this game of like two people running at each other, where if we both choose to do different things, we're better off than if we both choose to do the same thing. Okay. It's just that in this example, right, the payoffs like weren't exactly the same from those both of those situations, but we still ended up with multiple equilibrium. Okay. All right. 5 minutes left here. I think we'll save this for next class. I've got an example where I've got more than kind of 2 decisions. We'll talk about extensive form games tomorrow. We should have more than adequate time to kind of finish up some of this stuff I glossed over. So maybe we'll even start tomorrow with another prisoner's dilemma example, looking at these attack ads. I'll return to this research and development example, try to model in what if we have some patents that prevent each other from benefiting, and what would the payoffs look like there. We'll look at just one example, and I won't give this to you on a quiz or an exam, but just to kind of help you identify, like, sometimes there isn't a Nash equilibrium, and also how would you solve a game if it had more than 2 choices. And then we'll look at some extensive form game stuff, which is slightly different than what we talked about today. And if we have some time, I will then think about sequential decision games. We should have more than enough time to maybe work through some practice problems on Monday. But I would probably also try to reserve some time. I will probably start module 13 on Monday at the end of class. The module reading for module 13 still won't be due until Tuesday, though, like the first class that, really we would have the whole class period where we talk about it. But I may start it if we have time on Monday, just so it saves us some time on Tuesday and Wednesday, really on Wednesday, to kind of talk more about it in class. Okay. All right. Any questions on anything before we end the recording here today? Okay. All right. So like I said, this looks quite a bit different than what we've been doing. We'll need to be comfortable solving these normal form games. So once again, just working through more problems on Monday, I think will be beneficial. Module 10 and 11 and the 5 participation quizzes after today that we have this week, all due by the end of the day on Sunday. Okay. All right. Have a good weekend, and I'll see you Monday.